Hey, you. Ever just stop and really think about what space and time actually are? Fundamentally, I mean, they're
Mm.
just there, or seem to be, the backdrop for everything. But what if that backdrop is more like, well, stage dressing?
You sent over some really fascinating stuff from the 23rd Solvay Conference on Physics, the quantum structure of space and time. Seriously got me thinking.
No, it's definitely a rabbit hole. And the Solvay conferences, they have such a history, right? Always tackling the biggest, deepest questions in physics.
Right, like going way back.
Exactly. Think about the early ones, 1911, talking about radiation and the birth of quantum mechanics, pretty
Mhm.
much, or 1927, the famous one where they hashed out the interpretation of quantum theory.
Bohr, Einstein, all those guys arguing.
Precisely. And this more recent one, focusing on space and time itself. It's totally in that tradition. David Gross even said in his opening talk they wanted to capture that spirit of the really early game-changing meetings. I love that. Connecting back to the history. In Gross's phrase, the stormy marriage of quantum mechanics and relativity, that really stuck with me.
It's perfect, isn't it? Describes the situation so well. These two amazing theories, general relativity and quantum mechanics, but they just don't play nice together.
Yeah, they seem to describe the universe in totally different languages, and the material you shared makes it clear these aren't new problems. The questions are just as deep, maybe deeper than they were 100 years ago.
Absolutely. And that's really the core of this deep dive, isn't it? This pretty radical idea that maybe space and time, maybe they aren't fundamental.
Oh,
Yeah, that they could be emergent, that they bubble up from some deeper level of reality that doesn't necessarily have space and time built in from the start. It was a huge theme at the conference, according to the proceedings.
okay, emergent space-time. Let's try to break that down. So the basic problem is quantum mechanics for the small stuff, general relativity for gravity, and the big picture, and they clash hard.
Right. Quantum mechanics is all about probabilities, fuzziness, discrete packets of energy. General relativity is smooth space-time, geometry, determinism. They're built on fundamentally different principles.
It's not just finding one equation to rule them all, it's like the philosophies behind them are different.
Exactly. And out of that clash comes this idea, maybe the space-time of general relativity isn't the starting point. Maybe it's an approximation, an effective description. Nathan Seiberg's talk really focused on this.
Okay, so emergent space-time. It's like the wetness of water. Individual H2O molecules aren't wet, but put enough together, and wetness emerges as a property.
That's a great analogy, actually. Space-time could be like that collective property arising from more fundamental, non-spatiotemporal molecules of reality, whatever those might be.
Okay, mine's slightly blown already. And then there's this ambiguous space thing you mentioned from string theory, T-duality.
Right, yeah. That
Yeah.
adds another layer of weirdness. String theory has these things called dualities, where you can have two seemingly completely different descriptions of space-time geometry.
Different shapes, different sizes.
Potentially, yeah, different geometries. But the physics that happens in them turns out to be exactly the same. It's like having two different maps that look totally unalike, but always lead you to the same place.
So, which geometry is the real one?
That's the point. Maybe the question doesn't make sense at that fundamental level. Maybe the geometry itself is ambiguous. And it gets stranger when you try to look closely.
How so?
Well, the documents mention this. If you try to probe space at smaller and smaller scales, you need more and more energy, right?
Uh-huh. Makes sense. Higher energy is shorter wavelength.
But in string theory, if you pump enough energy into your probe, the probe itself starts acting like a bigger extended object, like a string getting longer.
Mm.
So instead of seeing finer detail, you just start blurring things out again.
Wait, so trying to look closer makes your magnifying glass effectively bigger.
Kind of, yeah. There seems to be a fundamental limit to how precisely you can resolve space-time structure. You hit a wall where looking closer actually means looking bigger in a sense.
That is counterintuitive. Wild. And this ties into the idea that even general covariance might not be fundamental, that cornerstone of Einstein's theory.
It's a possibility raised in the material, yes. General covariance is the principle that the laws of physics are the same for all observers, regardless of how they're moving or how space-time is curved.
Seems pretty fundamental.
It does. But if space-time itself isn't fundamental, but emerges, then maybe the rules governing how things behave within that emergent space-time, like general covariance, are also emergent properties, not baked in from the start.
Okay, My brain is definitely stretching now. Can we ground this a bit? You mentioned some examples of how space could emerge.
Sure, the sources give a few. An early, simpler one comes from studying 2D gravity using something called matrix models.
Matrix models, like arrays of numbers.
Exactly, just
Yeah.
matrices following quantum rules. And in certain limits, what pops out is an effective description that looks just like a two-dimensional space with gravity obeying general covariance.
So the space and its rules weren't put in, they just happened from the math of the matrices?
Pretty much. The spatial dimension and the gravitational rules emerged from the collective behavior of the matrix elements. It was a proof of principle in a simplified setting.
Okay, that helps. What about more complex examples?
A really big one, which the text implies was definitely discussed heavily at the conference, is the gauge-gravity duality, or AD-SCFT correspondence.
Ah, yes, add SCFT. Heard of it. Sounds important and confusing.
It's definitely both. But the core idea is this really shocking equivalence. On one side, you have a theory of gravity in a specific kind of curved space-time anti-de Sitter space, or ADS.
Okay, gravity in, say, 5 dimensions.
Right. And on the other side, you have a quantum field theory, without gravity living on the boundary of that space-time in one fewer dimension. So like a four-dimensional boundary.
A quantum theory, no gravity on the edge.
And the claim, the duality, is that these two descriptions are completely equivalent. They are different mathematical ways of describing the same underlying physics.
Wait, so the gravity theory in 5D is the quantum theory in 4D. How does that work?
That's the magic, and where emergence comes in. From the perspective of the boundary theory, the extraspatial dimension and gravity itself in the bulk spacetime are emergent phenomena. They arise from the complex interactions of the quantum fields living on the boundary.
Like a hologram, a 2D surface encoding a 3D image.
Exactly like a hologram. That's the perfect analogy. The boundary theory is like the holographic plate, and the higher dimensional spacetime with gravity is the projected image. The gravity and the extra dimension aren't in the plate itself, they emerge from it.
Okay, hologram analogy helps. Still feels like science fiction, but
Yeah.
okay. Any other examples?
The sources also mentioned the BFSS matrix model. This is another matrix-based quantum mechanics system, really simple in its setup.
More matrices.
Yep. But remarkably, the idea is that from the quantum dynamics of these matrices, you get the emergence of specifically one time dimension and 9 spatial dimensions.
9, not 3.
9 in this model. And then, even more incredibly, the 10th spatial dimension is supposed to emerge holographically, sort of like an AD-SCFT. So you start with basically 0 dimensions, just matrices interacting, and boom, 10 spacetime dimensions could potentially emerge.
My everyday experience feels very, very limited right now. Okay, so if space can emerge, the obvious next question has to be, what about time?
Exactly the question the physicists asked. If space is suspect, why not time? We usually lump them together as space-time, right? So if one part is emergent, maybe the other is too. Maybe the whole space-time concept is emergent.
Does that even make sense? How could time emerge? Everything happens in time.
It's definitely harder to wrap your head around. But the sources do mention at least one theoretical candidate discussed at the conference. It involves 2D quantum gravity again, but this time coupled to matter with a property called a central charge greater than 25.
Okay, technical terms, but what happens?
In those specific models, a particular component of the theory called the Liouville mode, it starts behaving mathematically like a time dimension. Its dynamics effectively create a time-like direction within the theory.
So time isn't put in by hand, but one part of the mathematical machinery becomes time.
Sort of, yeah. It suggests a mechanism, at least in that theoretical toy model, for how a time dimension could arise dynamically from something more fundamental that isn't itself time.
The Liouville mode.
Uh,
Okay, letting that one sink in. And the material also mentions something about lots of different ways to define string theory.
Yes, that was in the conclusion on emergent spacetime. It seems there are many different mathematical setups, different backgrounds, where string theory seems to work consistently.
So which one is right? Which one describes our universe?
That's the huge question. The text speculates that maybe this concept of large N related to the size of the matrices in those matrix models, basically how many fundamental components there are, maybe that plays a key role. Perhaps only theories with a large enough N can lead to macroscopic dimensions like the ones we see.
Large N. Another piece of the puzzle. This is just, it keeps getting deeper. And then the sources take it even further. The idea that maybe even quantum mechanics itself isn't the final word.
Right, just when you think it can't get more fundamental, they question the foundations of quantum theory. The text explicitly mentions that some physicists think quantum mechanics might need to be replaced.
Replaced. But It works so incredibly well. All our technology,
Oh,
electronics.
absolutely.
Yeah.
Its predictive power is stunning, but there are still those nagging issues,
Mm.
the clash with gravity, the measurement problem, the inherent randomness, things that make some researchers wonder if there's something underneath quantum mechanics.
Underneath, like what?
Well, the documents mention people like Adler exploring deterministic matrix models where quantum behavior might emerge statistically, or Gerard Hooft, who's long argued for determinism hiding beneath quantum randomness.
So the dice rolling god that Einstein didn't like, maybe the dice are just reflecting a mechanism we don't understand yet.
That's the kind of idea being explored, that the probabilities aren't fundamental, but come from a deeper, possibly deterministic, but incredibly complex or hidden layer. And Roger Penrose's idea is mentioned too.
Oh yeah, Penrose. He thinks gravity's involved, right?
Exactly. He suggests that gravity, which isn't properly included in standard quantum theory, might be the missing piece that explains how quantum possibilities collapse into definite realities, the state vector reduction.
So maybe unifying gravity and quantum mechanics will also solve some of quantum mechanics' own internal puzzles.
That's the hope for many. And there's one more hint mentioned in the discussion summary: the math itself,
How so?
the commutation relations in quantum mechanics, the rules saying you can't note position and momentum perfectly at the same time, that kind of thing.
Heisenberg uncertain.
Related, yeah. The underlying mathematical structure for those relations is the same type of structure called a Lie algebra that describes symmetries in physics, like rotations or boosts.
The math looks the same. Is that just a coincidence?
Or is it a clue?
Hmm.
That's the question raised. Does this mathematical echo hint at a deeper connection? Maybe quantum rules and spacetime symmetries were really just two sides of the same coin, stemming from a more unified underlying structure that we haven't grasped yet.
Wow. Okay. Let's try to pull this together, this deep dive into the Solvay proceedings. It shows physicists really pushing the boundaries, questioning everything we thought was solid.
Absolutely. Space, time, even quantum mechanics, all potentially up for grabs at fundamental concepts.
And replaced by this idea of emergence. Things bubbling up from a deeper, stranger level of reality described by things like string theory, matrix models, holography.
And crucially, these aren't just philosophical musings, right?
Mhm.
They're being investigated with serious mathematical tools. It's physics at the absolute cutting edge.
It really reframes everything, thinking that space and time are just effective descriptions, like the surface of an ocean, hiding the incredible complexity of the currents and ecosystems underneath.
That's a good way to put it. What we experience is real, but it might be the large-scale behavior of something much more intricate and less familiar.
It really makes you wonder, doesn't it? If our basic understanding of space and time could be emergent, how does that change how we see the universe, our place in it? Maybe reality is just fundamentally weirder and more connected than we can easily imagine.
It certainly suggests that possibility. The questions raised in these Solvay discussions feel like, well, maybe just the beginning of figuring out that deeper picture.
Makes you think. What else are we taking for granted? What other fundamental aspects of reality might turn out to be something completely different underneath? Gives you a lot to chew on.